What if I told you Earth wasn't always Earth? That the sky might have glowed a faint purple, the continents were jumbled up, flipped upside down, and life was so strange it didn't even need eyes or bones. No dinosaurs, no fish, no forests. Just a world so alien it feels like science fiction. But this isn't a movie. This is our planet, 600 million years ago, long before anything we'd recognize called it home. Welcome to Prehistoric Planet. This isn't just a timeline of rocks and fossils. It's the story of a living, breathing world that changed over 500 million years. A world reshaped by oceans, fire, and creatures weirder than anything in your wildest dreams. Before humans, before mammals, even before dinosaurs, Earth was a stranger place than we could ever imagine. Let's step into that world, starting with its earliest chapter, a time when life was just figuring out how to exist. Imagine a world with no predators, no sharp teeth, no claws, no battles for survival, just soft, strange shapes drifting through shallow oceans, swaying like kites caught in a gentle current. No crunch of bones underfoot, because bones don't exist yet. No chirping, roaring, or scurrying, just silence, broken only by the lap of waves over a planet that's still waking up. This is Earth, 600 million years ago, in a time called the Ediacaran period. It's the dawn of something big, the first large multicellular life. But these creatures, they're nothing like us or anything alive today. To understand this world, let's set the stage. Earth is coming off a rough patch. Just before the Ediacaran around 635 million years ago, the planet was locked in a deep freeze called Snowball Earth. Glaciers covered nearly everything, from pole to pole, according to research from geologists like Dr. Paul Hoffman at Harvard University. Oceans were capped with ice and life, mostly tiny microbes, clung to survival in pockets of open water or deep-sea vents. But as the planet warmed, volcanoes pumped carbon dioxide into the air, melting the ice and opening up the oceans. So the Ediacaran Earth is, wet. Almost all life exists in the seas because land is just a barren wasteland of rock and sand, with no plants or animals to soften it up. The continents are actually unrecognizable, lumped together in this supercontinent called Pannonia, which, by the way, is breaking apart. Fossils from places like Newfoundland, studied by researchers at the University of Cambridge, show coastlines totally teeming with strange life. And the skies? Well, they're low on oxygen, only about 10 to 20% of today's levels according to studies in Nature Geoscience. This makes the air feel thin, and the oceans honestly kind of sluggish, but hey, it's enough for something new to emerge. The water itself even looks different. Iron-rich sediments give the seas this reddish tint, almost like rust dissolved in liquid. Sunlight filters through, but it's weaker than what we see today, since the atmosphere scatters it differently. Some scientists, like Dr. Sanjoy Som from NASA, actually suggest the sky might have had a purplish hue because of methane and less oxygen. It's a world that feels totally alien, even to the life that inhabits it. But in these strange oceans, something incredible is happening. Life is getting bigger, bolder, and honestly a lot weirder. Enter the Ediacaran biota, the first large multicellular organisms that we actually know of. These aren't fish, worms, or jellyfish though. I mean, they might look a little bit like them. They're soft-bodied, boneless, and usually flat, living right on the ocean floor, glued to microbial mats. Basically slimy layers of bacteria that carpet the seabed. Fossils from sites like the Ediacara Hills in Australia, first discovered way back in 1946, give us a glimpse of these creatures. Paleontologists like Dr. Mary Drosser from UC Riverside have spent decades piecing together their story. Take Dickinsonia, for example, one of the real stars of the Ediacaran. It's this flat, oval-shaped thing, up to 4 feet long with ribbed segments, kind of like a quilt. Some fossils, preserved in Russia's White Sea, actually show it inching along the ocean floor, leaving behind these faint trails. Was it eating the microbial mat, absorbing nutrients through its skin? Scientists aren't really sure. Dickinsonia has no mouth, no eyes, no organs that we can recognize. A 2018 study in Science found traces of cholesterol-like molecules in its fossils, suggesting it might be an early animal. But you know, some folks argue it could be a giant protist or even a lichen-like hybrid. Then there's Charniodiscus, which looks like a feather or a frond anchored to the seabed. It sways in the currents, up to 6 feet tall, its branches covered in tiny, disc-like structures. Was it filtering food from the water, like a sea pen, or just soaking up dissolved nutrients? Fossils from Newfoundland's Mistaken Point, a UNESCO World Heritage Site, show communities of these fronds packed together, like an underwater forest. But they're not plants, and maybe not animals either. Some researchers, like Dr. Guy Narbonne from Queen's University, call them a failed experiment in life, unlike anything alive today. Other oddballs include Tribrachidium, a 3-armed disc that looks like an alien pinwheel, and Sprigina, a segmented creature some thought was an early worm, but others say might be closer to a jellyfish relative. These creatures are so bizarre that paleontologists debate whether they're ancestors to modern animals, or a dead-end branch on the tree of life. The Ediacaran is a puzzle, and every fossil raises more questions than answers. What's striking about the Ediacaran is how peaceful it seems. There's no evidence of predators, no bite marks on fossils, no signs of defenses like shells or spines. These creatures lived slow, simple lives. Dickinsonia might have glided over microbial mats, grazing like a living Roomba. Charniodiscus stood still, letting the ocean feed it. Life wasn't about competition yet, it was about existing. Scientists like Dr. Douglas Irwin from the Smithsonian Institution described this as a garden of Ediacara, a world where life coexisted without the struggle we associate with evolution. This peace was possible because the oceans were stable. Microbial mats provided food and structure, like a buffet in a home rolled into one. Oxygen levels, though low, were rising, thanks to cyanobacteria pumping out oxygen over millions of years. A 2016 study in Proceedings of the National Academy of Sciences suggests oxygen hit a tipping point around 600 million years ago, allowing larger bodies to form. But these creatures didn't need much energy. No brains, no muscles, no chase scenes. They were the first draft of complex life, and it worked, for a while. The Ediacaran also hints at something profound. Life was experimenting. Fossils show a range of shapes, discs, fronds, tubes, quilts, unlike the symmetry we see in later animals. Some, like Fractofusus, look like fractals, repeating patterns that defy classification. Were these creatures testing every possible way to be alive? Or were they limited by a world that wasn't ready for jaws, legs, or eyes? The fossil record doesn't tell us why they appeared, or why most vanished by the end of the Ediacaran. Hold up! If you're already blown away by these forgotten forms, these alien kites drifting through Earth's ancient oceans, then hit that subscribe button right now. We're just getting started, and trust me, it gets wilder. The kind of wild that crawls, bites, and explodes into life like nothing you've ever seen. Stick with us for the next chapter of Prehistoric Planet. Where did these creatures come from? That's honestly one of the biggest questions in paleontology. Before the Ediacaran, life was mostly microscopic. Bacteria, algae, maybe even some tiny sponges. Then, all of a sudden, we get Dickinsonia and its friends, some of them as big as a coffee table. There's no clear ancestor for them in the fossil record. A 2020 study in paleobiology suggests they might have evolved from microscopic larvae that got bigger as oxygen levels rose, but, we just don't have those missing link fossils to prove it. Some scientists, like Dr. Shuhai Xiao from Virginia Tech, propose that the Ediacaran biota weren't all animals. Dickinsonia might be, but Charniodiscus could actually be closer to a fungus or maybe a colonial organism. Others, like Dr. Jennifer Hoyle-Cuthill from the University of Tokyo, use computer models to argue they're a totally unique group, unrelated to modern life. The debate is still going on because Ediacaran fossils are rare, and they're often squished into flat impressions that really hide their true nature. Sites in places like South Australia, Namibia, and Russia give us some glimpses, but honestly, it's like trying to reconstruct a novel from just a single page. What's clear is that the Ediacaran was a turning point. Life went from single-celled blobs to complex, visible forms. The oceans became a stage for evolution's first big show, but the curtain was about to fall. By 541 million years ago, most Ediacaran creatures disappeared, replaced by the Cambrian Explosion, a burst of new life with shells, legs, and eyes. What wiped them out? Was it competition, a change in the oceans, or something we haven't found yet? Let's take a moment to soak this in. The Ediacaran Earth was a place of red oceans, purple skies, and creatures that defy our understanding of life. No predators hunted, no battles raged, just soft, strange shapes living in a quiet, alien sea. It's hard to picture a world so different from ours, where the rules of survival were still being written. Yet this was our planet, the cradle of complex life. These creatures, whether animals or something else, were pioneers. They thrived in a world low on oxygen, tethered to microbial mats with no need for speed or strength. But their time was short. The Ediacaran lasted about 60 million years, a blink in Earth's 4.6 billion-year history. By its end, the stage was set for a new act, one with claws, shells, and the first true fight for survival. This world raises big questions about life itself. Were the Ediacaran creatures a one-off, a weird detour in evolution? Or were they the first step toward everything that followed, from fish to dinosaurs to us? Their fossils, locked in ancient rocks, are like a message from a stranger, familiar yet impossible to fully understand. As we leave the Ediacaran's quiet oceans, think about those strange, soft-bodied creatures drifting through the red-tinged waves. Dickinsonia, Charniodiscus, Tribrachidium. What were they, really? Were they the earliest animals, our distant ancestors? Or were they something else entirely, a form of life with no living relatives at all? The answer might rewrite the story of how life began, and what it could become. Chapter 2. The Cambrian Explosion, spanning from about 541 to 485 million years ago. Imagine a quiet ocean, filled with soft, swaying creatures drifting along like living kites. Then, in a blink of geologic time, everything changes. Eyes pop into existence, scanning the water. Hard shells and spiky armor appear. Legs scuttle, claws snap, and suddenly, the seas are a battlefield. This is the Cambrian Explosion, a moment when life didn't just evolve, it slammed the gas pedal, rewriting the rules of survival. In just a few million years, Earth went from a peaceful garden to a wild, chaotic arena where predators hunted and prey fought back. Welcome to the Cambrian, where the modern animal kingdom was born, and the planet started to look like something we might recognize, if we squint. The Ediacaran world was strange, with its soft-bodied, boneless creatures gliding over microbial mats. But around 541 million years ago, something shifted. The fossil record lights up with a burst of new life forms, so sudden and dramatic it's called the Cambrian Explosion. Scientists like Dr. Douglas Irwin from the Smithsonian Institution describe it as evolution's Big Bang, a period when most major animal groups we know today, from worms to arthropods, appeared in a flash. Fossils from sites like the Burgess Shale in Canada and Chengjiang in China show a world transformed, teeming with creatures that had legs, eyes, and hard bodies for the first time. So why do we call it an explosion? Well, in just 10 to 20 million years, which is honestly a blink of an eye compared to Earth's 4.6 billion-year history, life went from really simple forms to just wildly complex creatures. Before the Cambrian period, most organisms were, just blobs or fronds, but now suddenly you've got animals with skeletons, joints, and even brains. The oceans, which were once pretty calm, became a whole stage for swimming, burrowing, and hunting. The planet itself actually helped set the scene. Oxygen levels, which were super low back in the Ediacaran, kept rising, eventually reaching maybe 20 to 30% of what we have today, according to a 2018 study in Science. This boost in oxygen gave animals the energy they needed to grow bigger and move faster. The breakup of the Pannonia supercontinent, which geologists like Dr. Ian Dalziel at the University of Texas have studied, created all these new coastlines and shallow seas, and honestly, these were just perfect nurseries for new life to thrive. But the Cambrian wasn't just about more oxygen or space. Something deeper was at play. Genetic studies, like those from Dr. Eric Sperling at Stanford University, suggest animals developed new toolkits. Genes like Hox genes that control body plans. These genes let creatures experiment with new shapes like segmented bodies or paired legs. It's as if evolution unlocked a cheat code, letting life build complex animals almost overnight. But what triggered this frenzy? That's a question we'll circle back to. Let's meet the creatures that made the Cambrian so wild. First up, trilobites. These guys were the rock stars of the ocean floor, scuttling around like armored beetles. With their hard exoskeletons and compound eyes, some of the first eyes ever, trilobites were built to survive. Fossils from the Burgess Shale, discovered in 1909 by Charles Walcott, show trilobites in staggering variety, some as small as a dime, others as big as a dinner plate. Trilobites had segmented bodies, jointed legs, and, well, they could even roll up like pill bugs to protect themselves. A 2020 study in paleobiology estimates there were thousands of trilobite species crawling across every continent's seas, munching on microbes or small critters. Then there's Anomalocaris, the Cambrian's apex predator. Just imagine a shrimp-like monster up to 3 feet long, with a circular mouth full of jagged plates and 2 claw-like appendages for grabbing prey. Fossils from Chengjiang, China, studied by Dr. Alison Daly at the University of Lausanne, show Anomalocaris was a terror, hunting soft-bodied animals like worms or early fish. Its eyes, about the size of marbles, had thousands of lenses giving it hawk-like vision, according to a 2011 Nature study. This was no gentle grazer, it was the T-Rex of its time, ruling the seas. Other weirdos filled the oceans. Wiwaxia looked like a spiky pincushion covered in scales and bristles, possibly scraping food off rocks. Hallucigenia, a tiny worm with legs and spines, baffled scientists for decades. Early reconstructions had it walking upside down. Fossils from Canada's Burgess Shale, analyzed by Dr. Jean-Bernard Caron at the Royal Ontario Museum, reveal its true form, a quirky crawler with a flexible body. Then there's Opabinia with 5 eyes and a claw-tipped trunk like a vacuum cleaner from an alien planet. These creatures weren't just diverse, they were bizarre, testing every possible way to swim, eat, and survive. The Cambrian wasn't just about weird animals, it introduced the building blocks of modern life. Exoskeletons made of chitin or calcium carbonate gave creatures like trilobites and early mollusks protection and structure. Eyes, from simple light-sensing spots to Anomalocaris' complex lenses, really changed the game. Suddenly, animals could actually see predators or prey, making the oceans a much more dangerous place. Legs and jointed appendages let creatures like Morella, a delicate arthropod, scuttle or swim with, surprising precision. This was also the birth of predation. Back in the Ediacaran, life was, pretty peaceful. No teeth, no claws. Now Anomalocaris and others were hunting, leaving bite marks on trilobite fossils, as found in Australia's Emu Bay Shale. Prey fought back with armor or by burrowing, sparking an evolutionary arms race. A 2019 study in Nature Communications suggests this predator-prey dynamic drove the explosion of diversity. Survive or die trying. Food webs grew complex, with scavengers, filter feeders, and hunters all carving out roles. The oceans themselves were changing. Deep-sea volcanoes, studied by geochemists like Dr. Rachel Wood at the University of Edinburgh, spewed minerals that fueled microbial blooms, feeding the food chain. Shallow seas warmed by a brighter sun teemed with life. Fossils from Chengjiang, preserved in exquisite detail, show soft tissues like muscles and guts, giving us a window into these ancient ecosystems. It's like the planet threw a party, and every creature showed up with a new trick. How do we know all this? The Cambrian left behind some of the best fossil sites on Earth. The Burgess Shale in British Columbia, Canada, is kind of a superstar. Buried in a mudslide over 500 million years ago, it preserved creatures in just stunning detail, even their eyes and antennae. Discovered more than a century ago, it's been studied by paleontologists like Dr. Derek Briggs at Yale, revealing more than 200 species. Chengjiang in China, found back in the 1980s, is actually even older, dating to about 518 million years ago. Its fossils, according to a 2022 Science Advances study, show colors and textures hinting at how these animals looked in life. These sites are like time capsules, capturing a snapshot of the Cambrian seas. But they also raise questions. Why are these fossils so well preserved? Was it just luck, or did the Cambrian's oceans have unique chemistry that locked life in stone? And why do we see so many body plans that vanished soon after? So what made the Cambrian explosion possible? Well, scientists point to a mix of factors. Rising oxygen, according to a 2016 geobiology study, gave animals the energy they needed for complex bodies. And new habitats from breaking continents provided space to experiment. But, the real spark might have been genetic. Hox genes, which act kind of like blueprints for body segments, became more sophisticated, letting animals build heads, tails, and limbs. A 2023 Nature study by Dr. Jakob Winther suggests these genes switched on in multiple lineages at once, triggering a cascade of diversity. This wasn't a single event, but actually a series of bursts. Some groups, like sponges and jellyfish, predate the Cambrian, but arthropods, mollusks, and early chordates, our ancestors, exploded here. Fossils of Pikaia, a small eel-like creature from the Burgess Shale, hint at the origins of vertebrates, with a notochord that's, a precursor to our spine. Every major animal phylum, from worms to crabs, got its start here. But why did it take 3 billion years of microbes to reach this point? Picture the Cambrian seas. A swarm of trilobites scuttles across the ocean floor, their compound eyes glinting. Above, Anomalocaris glides, its claws snapping at a fleeing Wiwaxia. Opabinia waves its bizarre trunk, snatching bits of food. Deep-sea volcanoes glow faintly, their heat stirring currents that carry nutrients to this frenzy of life. It's not the quiet Ediacaran anymore. This is a world of motion, hunger, and survival. The Cambrian explosion wasn't just about new creatures, it was about new ways of living. Predation forced animals to adapt, faster, tougher, smarter. The oceans became a testing ground where evolution tried every trick in the book. Some worked, like trilobites, which thrived for 270 million years. Others, like hallucigenia, faded fast. It's a reminder that evolution isn't a straight line, it's a wild, messy experiment. This world feels alien yet familiar. The Cambrian laid the foundation for every animal alive today, from ants to whales to us. But it also left behind mysteries. Why did some body plans survive while others vanished? And what happened to the Ediacaran creatures? Did they evolve into these new forms, or were they As we leave the Cambrian's chaotic seas, think about this. In just a few million years, life went from soft blobs to armored predators with eyes and claws. Trilobites swarmed, Anomalocaris hunted, and the seeds of our own backbone were sown. But why did evolution explode then, after billions of years of silence? Was it oxygen, genes, or something we haven't uncovered? The answer might reveal why life looks the way it does, and what it could have been. Chapter 3. The Ordovician to Devonian, 485–359 million years ago. Picture an Earth still wild and unfamiliar, where oceans teem with strange creatures, but the land is a barren desert of rock and dust. Then, slowly, life starts to change. Coral reefs rise like underwater cities. The first green plants creep onto shore, painting the continents with life. Fish grow jaws, then legs, and some even dare to crawl out of the water. But this isn't just a story of beginnings, it's also one of endings, with a mass extinction that nearly wipes the slate clean. Welcome to the Ordovician, Silurian, and Devonian periods, a 126 million-year saga of first forests, first fish, and a fish that walked. This is when life took its boldest steps yet, from the seas to the land, setting the stage for everything to come. The Ordovician. Oceans alive, land empty. Let's start 485 million years ago in the Ordovician period. The Cambrian Explosion filled the seas with trilobites, worms, and predators like Ediacaran, but the Ordovician takes it up a notch. The oceans are bustling like a cosmic aquarium, one of the biggest stars? Coral reefs. These weren't like today's colorful reefs, they were built by strange creatures like bryozoans and early corals, alongside sponges and algae. Fossils from places like Anticosti Island in Canada, studied by researchers like Dr. André Desrochers at the University of Ottawa, show reefs stretching for miles, home to swarms of life. Among the new arrivals are jawless fish, the first vertebrates, animals with backbones. These aren't your typical fish. Astraspis and Arandaspis, found in fossils from Colorado and Australia, were armored, eel-like creatures, some up to a foot long, with bony plates covering their heads. They had no jaws, just a slit for a mouth to suck in tiny bits of food, like underwater vacuum cleaners. A 2019 study in Nature suggests their armor protected them from predators like giant sea scorpions, eurypterids, that prowled the seas, some as long as 8 feet, with pincers and stinging tails, per fossils from New York's Silurian rocks. The Ordovician seas were diverse. Trilobites, still thriving, shared space with nautiloids, squid-like creatures with long conical shells, some 10 feet long. Fossils from Morocco, analyzed by Dr. Christian Klug at the University of Zurich, show these cephalopods jetting through the water, snatching prey with tentacles. Starfish and brittle stars crawled the ocean floor, while brachiopods, clam-like animals, filtered food in huge colonies. Oxygen levels, now closer to 30% of modern levels per a 2020 geobiology study, fueled this boom, and warm, shallow seas from drifting continents like Laurentia, early North America, created perfect conditions. But then, disaster struck. Around 443 million years ago, the Ordovician-Silurian mass extinction wiped out 85% of species. Scientists like Dr. David Bond at the University of Hull point to a sudden cooling, possibly from volcanic ash blocking sunlight or shifting ocean currents as continents moved. Reefs collapsed, trilobites took a hit, and many jawless fish vanished. The cause isn't fully clear. Some evidence from science advances suggests falling oxygen levels, but it was a brutal reset. What would rise from the ashes? The Silurian. Greening the land. Fast forward to the Silurian, starting 443 million years ago. The planet's recovering, and life's ready to try something new, colonizing land. The continents are still mostly bare, think rocky deserts under a pale sky, but the first plants appear, tiny and tough. Cooksonia, a plant no taller than a few inches, is the pioneer. Fossils from Scotland, studied by Dr. Paul Kenrick at the Natural History Museum in London, show it had simple stems, no leaves, and spore sacs for reproduction. These plants hugged wet riverbanks, their roots stabilizing soil and pulling in nutrients, per a 2018 Nature Plants study. Why now? Rising oxygen, warmer climates, and a thinning atmosphere let sunlight reach the ground, fueling photosynthesis. These plants weren't alone. Fungi, like those found in 407 million-year-old fossils from Rhynie Chert in Scotland, partnered with them, trading nutrients in a symbiotic dance. Arthropods, early relatives of spiders and centipedes, followed. Pneumodesmus, a millipede from Scotland, is one of the oldest known land animals, its tiny legs scooting across damp soil 428 million years ago, per a 2004 science study. In the seas, life rebounds. Jawless fish like Pteraspis swim in schools, their streamlined armor gleaming. Early jawed fish like Entelognathus from China appear late in the Silurian, with bony plates hinting at the predators to come, per a 2013 Nature study. Reefs rebuild, smaller but vibrant, hosting brachiopods and crinoids, sea lilies that look like feathery flowers. Sea scorpions still lurk, but the stage is set for a new era. The Silurian feels like a bridge, life's testing land, but the oceans still rule. What happens when fish take over? The Devonian, the Age of Fish. By 419 million years ago, the Devonian period begins, and it's nicknamed the Age of Fish, for a reason. The seas are a fish paradise, packed with creatures that make the Cambrian look tame. Jawed fish explode in diversity. Dunkleosteus, a 30-foot armored giant, is the king of predators. Fossils from Ohio's Cleveland Shale, studied by Dr. John Long at Flinders University, show its massive jaws could crush bone like a hydraulic press, with a bite force rivaling a T-Rex. This wasn't a fish you'd want to meet. It hunted sharks and other fish with ease. Other players include Bothriollepis, a flat, armored fish with jointed fins, scooting along riverbeds, and Cladosalash, an early shark with sleek lines and sharp teeth, per fossils from Wyoming. Lobe-finned fish, like Eusthenopteron, had sturdy fins with bones hinting at limbs, a clue to what's coming. These fish shared seas with trilobites now declining and ammonites, spiral-shelled cephalopods that bobbed like living buoys. On land, forests take root. Archaeopteryx, a tree up to 100 feet tall, forms the first true forests, per fossils from New York studied by Dr. William Stein at Binghamton University. These trees had leaves, deep roots and wood, pulling carbon dioxide from the air and boosting oxygen to near-modern levels, per a 2019 Nature Geoscience study. Their shade sheltered early insects like Meganeura, dragonfly-like bugs with 2-foot wingspans found in French fossils. Spiders and mites scurried underfoot, building the first terrestrial food webs. But the Devonian's biggest twist happens in the shallows. Tiktaalik, a fish with fins that could bend like elbows, crawls onto muddy riverbanks 375 million years ago. Fossils from Canada's Ellesmere Island, discovered by Dr. Neil Shubin at the University of Chicago, show it had a neck, ribs and lungs. Half fish, half land animal. Tiktaalik could push itself up maybe to escape predators or hunt insects, per a 2006 Nature study. It's not alone. Acanthostega and Ichthyostega, also from Devonian rocks, had legs and toes, waddling in swamps. These are the ancestors of amphibians, reptiles and us. Life's bold leap to land. The move to land was huge. Why leave the water? Shallow seas were crowded with predators like Dunkleosteus, pushing some fish to explore riverbanks. Plants like Cooksonia and Archaeopteryx stabilized soil and provided food, tempting adventurers. Lungs, already present in lobe-finned fish for gulping air in low-oxygen waters, helped them survive on land, per a 2021 Science Advances study. Tiktaalik and its cousins weren't planning to conquer land, they were just surviving, one muddy step at a time. But land wasn't easy, no trees meant no shade, and early plants were sparse. Fossils from Greenland show Acanthostega lived in swampy pools, not dry land, suggesting a gradual transition. Insects had an easier time. Small bodies and exoskeletons let them scurry without drying out. By the late Devonian, ecosystems were forming. Plants fed insects fed early tetrapods, and the land started to hum with life. The Devonian wasn't all triumphs. Another mass extinction hit around 359 million years ago, linked to climate cooling and falling oxygen, per a 2020 Science study. Dunkleosteus and many placoderms vanished, but tetrapods and insects survived, ready to take over. The Devonian set the stage for land life, but why did fish evolve legs before forests fully formed? A world of giants and pioneers. Picture the Devonian. In the seas, Dunkleosteus slices through schools of fish, its armor glinting. Coral reefs pulse with crinoids and ammonites. On land, Archaeopteryx forests cast shadows over swamps where Tiktaalik crawls, its fins splashing in mud. Giant sea scorpions lurk in estuaries, while dragonfly-like insects buzz overhead. This is a world of giants in the water and pioneers on land, where life's testing new frontiers. The Ordovician gave us reefs and jawless fish. The Silurian brought green to the continents. The Devonian pushed life further, with jaws, legs, and forests. But it's also a world of fragility. Extinctions remind us nothing's guaranteed. Tiktaalik's story is especially wild. A fish that walked bridging sea and land, leading to every land vertebrate today. It's humbling to think our ancestors were splashing in Devonian mud. As we leave the Devonian swamps and seas, think about Tiktaalik, that fish with legs, crawling onto a world still half empty. Forests were just starting, insects were new, yet fish were already growing limbs. Why did evolution push them onto land before trees even took hold? Was it desperation, opportunity, or something deeper in their genes? The answer might show us why life dares to take such wild leaps, and what it might try next. Picture a world where swamps stretch as far as the eye can see, from pole to pole, under a steamy, oxygen-rich sky. Giant dragonflies with wingspans like seagulls buzz through the air. Millipedes the size of crocodiles lumber through dense forests of towering ferns. This is the Carboniferous, a time when Earth was a greenhouse jungle, teeming with life unlike anything we know today. But then the planet shifts. The swamps dry up, reptiles take over, and our earliest mammal-like ancestors appear, only to face the greatest catastrophe life has ever seen, the Great Dying. Welcome to the Carboniferous and Permian periods, a 107 million-year journey of lush forests, giant bugs, and a near apocalypse that reshaped life forever. Let's dive into the Carboniferous, starting 359 million years ago. The Devonian gave us forests and walking fish, but the Carboniferous turns the dial to 11. The continents are locked into a supercontinent called Pangaea, slowly forming as landmasses like Laurentia and Gondwana collide, per studies by Dr. Christopher Scotese at Northwestern University. This creates vast wet lowlands perfect for swamps. These aren't ordinary swamps. They're dense tropical jungles of giant ferns, club mosses, and horsetails, some trees soaring 100 feet high like Lepidodendron and Sigillaria, found in fossils from Illinois coal mines. Why so lush? Oxygen levels are sky-high, reaching 35% compared to today's 21%, according to a 2018 geology study. Plants like Archaeopteris from the Devonian kept pulling carbon dioxide from the air, burying it in swamps that later turned into coal, hence the name Carboniferous, meaning coal-bearing. This oxygen surplus fueled life in wild ways. Insects, which breathed through tubes in their bodies, grew massive because high oxygen let them take in more air. Fossils from France, studied by Dr. Matthew Clapham at UC Santa Cruz, show Meganeura, a dragonfly-like insect with a 2-foot wingspan, darting through the air. Arthropleura, a millipede up to 8 feet long, crawled through the undergrowth, its armored body crunching leaves. Amphibians ruled the land, thriving in the wet. Ariops, a 6-foot-long predator with a wide, toothy mouth, hunted in swamps, per fossils from Texas. Early reptiles appeared like Halonimus, a lizard-like creature from Nova Scotia, laying eggs with tough shells that didn't need water to survive, a game-changer per a 2020 paleobiology study. In the seas, sharks like Stethocanthus, with a weird anvil-shaped fin, prowled alongside nautiloids and early bony fish. Coral reefs, rebuilt after the Devonian extinction, teemed with crinoids and brachiopods per fossils from Australia's Great Barrier Reef precursors. The Carboniferous was a boom time. Forests pumped out oxygen, insects and amphibians diversified, and life seemed unstoppable. But the climate was shifting. By the late Carboniferous around 300 million years ago, Pangaea's formation dried out parts of the interior, and glaciers began forming in the south, per Dr. Isabel Montanez's research at UC Davis. The stage was set for change. Would the Swamp Kings adapt? Fast forward to the Permian, starting 299 million years ago. Pangaea is now a massive supercontinent, stretching from pole to pole, with deserts and mountains dominating its heart. The lush Carboniferous swamps shrink, replaced by drier forests of conifers and seed ferns, better suited to the changing climate per fossils from South Africa's Karoo Basin. Oxygen levels drop slightly to about 25%, and the air feels harsher, per a 2019 Nature Geoscience study. Life adapts and reptiles take center stage. Unlike amphibians, which needed water to lay eggs, reptiles like Dimetrodon thrived in the drier world. Dimetrodon, found in Texas fossils, wasn't a dinosaur, but a synapsid, an early relative of mammals. Its sail-like fin, which could reach up to 6 feet tall, helped regulate body temperature, according to Dr. Robert Backer's studies. It hunted with sharp teeth, preying on amphibians and early reptiles. Other synapsids, like Edaphosaurus, a plant eater with a similar sail, grazed on tough plants. These creatures, studied by Dr. Jennifer Botha at the University of the Witwatersrand, are actually our ancestors, mammal-like reptiles with traits like warm-bloodedness just starting to emerge. Insects were still giants, but, they faced new challenges. Meganeuropsis, another huge dragonfly, soared over drying forests, as shown by Illinois fossils. On land, Early conifers like Walchia spread and their seeds survived harsh conditions, unlike the spore-based plants of the Carboniferous. In the seas, trilobites dwindled, but ammonites and bony fish really flourished. Giant sea scorpions were gone, replaced by predators like Orthocanthus, a shark with a spiked tail according to fossils from New Mexico. The Permian was honestly a time of transition. Reptiles and synapsids outcompeted amphibians, setting the stage for dinosaurs and mammals. But the climate was unstable. Fossils from Antarctica show glaciers growing, while deserts spread in Pangaea's interior, according to a 2021 Science Advances study. Life was diversifying, but trouble was brewing. Something catastrophic was coming. If you're still watching, you're one of the rare minds that wonders what came before us. Before dinosaurs, before anything we'd recognize. These swampy forests and sail-backed reptiles are Earth's forgotten chapters. Share this video with someone who still thinks dinosaurs were the first rulers of the planet. Let's show them the real story of our world's wild past. The Great Dying Earth's worst extinction. Around 252 million years ago, the Permian ends with a bang, or rather a collapse. The Permian Triassic mass extinction, dubbed the Great Dying, was the worst in Earth's history, wiping out 90 to 95% of species. Fossils from South Africa's Karoo Basin, studied by Dr. Roger Smith at the University of Cape Town, show a sudden drop in diversity. Trilobites vanished completely. Most synapsids, amphibians and marine life like reefs and ammonites were decimated. So what caused it? The smoking gun points to the Siberian Traps, a massive volcanic region in what's now Russia. For about 2 million years, volcanoes erupted, spewing lava across an area the size of Australia. According to a 2020 Nature Geoscience study, they released billions of tons of carbon dioxide, methane and sulfur, superheating the planet by up to 10 degrees Celsius. Oceans acidified, oxygen plummeted to just 10% of modern levels, and toxic gases choked the air, based on Dr. Lee Kump's research at Penn State. Fossils from China show marine life suffocating as oxygen vanished, while land animals faced scorching heat and collapsing food chains. The evidence is, well, stark. A 2018 science study found a spike in mercury in rocks from the extinction boundary, a sign of volcanic fallout. Fossil pollen from Greenland shows forests dying off, replaced by fungi feeding on decay. The Great Dying wasn't instant, it actually took tens of thousands of years, kind of a slow-motion apocalypse. Synapsids like Lystrosaurus, a pig-sized burrower, survived, possibly because they could hide underground according to a 2022 paleobiology study. Some reptiles and early archosaurs, dinosaur ancestors, also scraped through, but honestly, the world was a shadow of its former self. Picture the Carboniferous endless swamps under a hazy, oxygen-rich sky where Arthropleura crawls like a tank and Meganeura hums overhead. Amphibians splash in pools while early reptiles dart through ferns. Then the Permian deserts stretch across Pangaea, Dimetrodon stalks prey under a harsh sun and conifers dot the landscape. By the end, volcanoes in Siberia erupt, blanketing the sky in ash, turning oceans to acid and leaving a scarred planet. This was a world of extremes. Lush jungles to barren wastes, giant insects to mammal-like reptiles. The Carboniferous built towering forests that, still fuel our coal plants today. The Permian tested life with aridity and heat, giving rise to our ancestors. But the Great Dying nearly ended it all, leaving only the toughest survivors. It's honestly humbling to think we're here because Lystrosaurus, a stubby, beaky creature, clung to life. As we leave the swamps of the Carboniferous and the ashes of the Permian, just think about the Great Dying. It erased 95% of life, reefs, forests, giants. Yet a few scrappy creatures, often the ugliest ones like Lystrosaurus, made it through. Why did nearly everything die? But these oddballs survived. Was it luck, toughness, or, well, something else? The answer might reveal what it takes to endure the end of the world, and what comes next. The Triassic period, stretching from 252 to 201 million years ago, marks a whole new chapter in the story of life. Imagine a world scorched and silent, picking up the pieces after the worst catastrophe life has ever faced. The air is hot, the land is parched, and the scars of the great dying linger like ghosts. But in this harsh, empty world, something stirs. Survivors creep out of burrows and swamps, ready to claim the earth. They're not the gentle creatures of the past. These are monsters. Scaly archosaurs stalk the deserts, giant amphibians lurk in rivers, and among them, the first dinosaurs take their tentative steps, alongside the earliest flickers of our own mammal ancestors, scurrying in the shadows. Welcome to the Triassic, a 51-million-year chapter of recovery, reinvention, and the rise of the creatures that would rule the planet. A scorched Earth recovers. The Triassic begins 252 million years ago, right after the Permian's Great Dying wiped out 95% of life. The planet is a wreck. Fossils from South Africa's Karoo Basin, studied by Dr. Jennifer Botha at the University of the Witwatersrand, show a world nearly empty of life. Forests are gone, replaced by sparse ferns and seed plants. Oceans are recovering, but reefs are rare, and oxygen levels hover around 15–20% per a 2020 Nature Geoscience study, low enough to make breathing feel like a chore. Pangaea, the supercontinent, dominates, stretching from pole to pole. Its interior is a brutal desert, baked by a sun unfiltered by lush vegetation, with temperatures swinging from scorching days to chilly nights, per Dr. Christopher Scatesi's paleoclimate models. The Siberian Traps volcanoes, which triggered the Great Dying, are quieting down, but their legacy lingers. Carbon dioxide levels are high, making the climate hot and unstable, with monsoons flooding coastal areas while deserts parch the interior, per a 2019 Science Advances study. Life clings to riverbanks and coasts where water and plants offer a lifeline. Survivors like Lystrosaurus, a pig-sized synapsid with a beaky face, dominate early Triassic fossils, found everywhere from Antarctica to China. This tough burrower, studied by Dr. Roger Smith at the University of Cape Town, survived by hiding underground, eating tough plants and shrugging off the heat. The oceans, too, are clawing back. Ammonites, spiral-shelled cephalopods rebound quickly, per fossils from Nevada. Early fish like Soricthus, sleek and predatory, swim in shallow seas. But the world feels fragile. Ecosystems are simple, food chains short. The Great Dying left a blank slate, and life's ready to write a new story. Who will take the lead? Enter the archosaurs, reptiles that would shape the future. These ruling reptiles include the ancestors of crocodiles, pterosaurs, dinosaurs, and birds. Fossils from Poland's Holy Cross Mountains, studied by Dr. Grzegorz Niedzwiecki at Uppsala University, show early archosaurs like Silosaurus, a 7-foot-long reptile with a long neck and nimble legs. It wasn't a dinosaur but a close cousin, eating plants or insects in river valleys. Archosaurs were versatile, thriving in the Triassic's harsh conditions, per a 2021 Nature study. In the seas and rivers, archosaurs got weird. Phytosaurs looked like crocodiles but weren't related, with long snouts full of sharp teeth, per fossils from Arizona's petrified forest. They ambushed fish and amphibians, ruling waterways. On land, Rauisuchians like Postosuchus, a 20-foot predator with dagger-like teeth, stalked prey, per Texas fossils studied by Dr. William Parker at Petrified Forest National Park. These weren't dinosaurs either, but they set the tone. Big, scaly, and fierce. Other reptiles joined the fray. Tanistropheus, found in Swiss and Chinese fossils, had a neck longer than its body, up to 10 feet, possibly for snatching fish from shallow waters, per a 2020 Current Biology study. Hyperodapodon, a beaky, plant-eating reptile, scurried in herds, its fossils common in Brazil. The Triassic was a proving ground for reptiles, with archosaurs leading the charge, but something even more iconic was emerging. Around 230 million years ago, the first true dinosaurs appear. They're not the giants we imagine, no T-Rex or Brontosaurus yet. These are small, nimble creatures, often no bigger than a dog. Eoraptor, found in Argentina's Isquigualasto Formation, was a 3-foot-long predator with sharp teeth, running on 2 legs, per Dr. Paul Serino's studies at the University of Chicago. Herrerasaurus, another early dinosaur from the same site, was bigger, up to 20 feet, and hunted smaller reptiles. Both were theropods, early cousins of later carnivores like Velociraptor. Plant-eaters emerged too. Platyosaurus, a 20-foot-long dinosaur from Germany, had a long neck and small head, munching ferns in herds, per fossils studied by Dr. Martin Sander at the University of Bonn. These weren't massive sauropods yet, but they hint at what's coming. Dinosaurs were fast and adaptable, thriving in Pangaea's varied climates, wet coasts, dry plains, and river valleys, per a 2018 paleobiology study. Their secret? Efficient lungs and lightweight bones, letting them move quickly and survive tough conditions. Unlike the sluggish amphibians they outcompeted, the skies saw action too. Tinosaurus, an early pterosaur from Italy, had a 2-foot wingspan, gliding over deserts to snatch insects, per fossils studied by Dr. Fabio Dalla Vecchia. These flying reptiles, archosaur cousins, were the first vertebrates to take flight, beating birds by millions of years. Meanwhile, massive amphibians like Mastodonsaurus, a 20-foot predator with a flat, toothy head, lurked in rivers, eating anything that swam by per German fossils. Here's the twist. Amid these scaly monsters, our own ancestors appear. The Triassic sees the first mammals, tiny rodent-like creatures descended from synapsids like Lystrosaurus. Morganucodon, found in Welsh and Chinese fossils, was the size of a mouse, with sharp teeth for eating insects, per Dr. Neil Shubin's research at the University of Chicago. These early mammals were nocturnal, hiding in burrows to avoid predators like Pastosuchus, per a 2022 Nature study. They had fur, and likely nursed their young, traits that set them apart from reptiles. Other mammal-like synapsids like Synagnathus, a dog-sized carnivore from South Africa, were more common but not true mammals. They had mammal traits like differentiated teeth, but were outshone by reptiles per Dr. Jennifer Botha's studies. These creatures scurried in the shadows, biding their time. Pangaea shaped the Triassic story. Its vast size created extreme climates. The interior was a scorching desert with dunes stretching for miles. Coastal areas were wetter, with monsoons feeding rivers where phytosaurs and Mastodonsaurus hunted. Ferns, cycads, and ginkgos dominated, replacing the Carboniferous' swampy giants. These plants supported herbivores like Plateosaurus, which in turn fed predators like Herrerasaurus. The oceans, though simpler than before, were lively. Nothosaurus, a seal-like reptile, swam in shallow seas. Ichthyosaurs, dolphin-like reptiles, gave birth to live young. Ammonites and clams thrived, but reefs were still recovering. The Triassic was a world of contrasts: desolate deserts, lush riverbanks, and seas teeming with new predators. Another extinction loomed at the end. Around 201 million years ago, the Triassic-Jurassic extinction wiped out 70–80% of species. But dinosaurs survived, ready to dominate. What gave them the edge? Picture the Triassic. A desolate desert stretches under a hazy sky, broken by rivers where phytosaurs snap at fish. Plateosaurus herds munch ferns while Eoraptor darts after prey. Patinosaurus glides above, casting long shadows. In the underbrush, Morganucodon scurries, a tiny mammal hiding from monsters. This is a world recovering from near death where life fights to rebuild. The Triassic was a crucible. The Great Dying left a battered planet, but archosaurs, dinosaurs, and early mammals rose to meet the challenge. Dinosaurs, small but scrappy, laid the groundwork for their Jurassic reign. Mammals, though, stayed small, sneaking through the night. The extinction cleared the way for dinosaurs to rule, but our ancestors survived. As we leave the Triassic's deserts and rivers, think about this. Dinosaurs began their rise, while our mammal ancestors hid in the dark, no bigger than mice. Why did dinosaurs thrive, growing bolder and bigger while our kin stayed small and scared? Was it luck, biology, or something about the world itself? The answer might show us why some survive and others dominate. Picture a world where giants roam, a land of thundering footsteps, where long-necked dinosaurs stretch toward the treetops and winged reptiles soar above lush forests. The scars of the Triassic's harsh deserts are fading, replaced by green plains and steamy jungles. The supercontinent Pangaea is cracking apart, birthing new oceans and filling the air with moisture. This is the Jurassic, a 56-million-year chapter where dinosaurs don't just survive, they dominate. Sauropods grow to sizes that defy imagination, pterosaurs rule the skies, and the seas swarm with monsters of their own. But amid this spectacle, a question lingers. Why did these giants get so big, yet never develop the smarts we see in later creatures? Let's step into the Jurassic and find out. The Jurassic begins 201 million years ago, after the Triassic-Jurassic extinction cleared out many of the archosaurs and amphibians that ruled before. The survivors, dinosaurs, pterosaurs, and early mammals, are ready to take over. Pangaea, the massive supercontinent, is starting to split, with cracks forming between what will become North America, Africa, and South America, per studies by Dr. Christopher Scotese at Northwestern University. These rifts create new coastlines and shallow seas, flooding the land with moisture. The climate is warm and humid, with no polar ice caps, according to oxygen isotope studies from fossil shells published in Science, 2018. Temperatures average 5–10 degrees Celsius warmer than today, fostering lush vegetation. Ferns, cycads, and conifers dominate, forming dense forests and open plains. Fossils from the Morrison Formation in western North America, studied by Dr. John Foster at the Utah Museum of Natural History, show towering ginkgos and tree ferns alongside horsetails in swampy lowlands. This greenery supports massive herbivores, which in turn feed predators. Oxygen levels stabilize at around 20–25%, close to modern levels, per a 2020 geobiology study, giving animals the energy to grow big. The Jurassic Earth is a paradise for life, with rivers teeming, forests buzzing, and seas alive with new players, but it's the dinosaurs that steal the show. If the Jurassic has a mascot, it's the sauropod, those long-necked, long-tailed giants that define the period. These are the biggest land animals ever, some weighing as much as 10 elephants. Brachiosaurus, found in Colorado's Morrison Formation, stood 40 feet tall, its neck reaching treetops like a living crane, per Dr. Kenneth Carpenter's research at the Denver Museum of Nature and Science. Diplodocus, another Morrison star, stretched up to 90 feet long, its whip-like tail balancing a slender body. Fossils show it could rear up to browse high branches, eating tons of ferns and cycads daily, per a 2019 paleobiology study. Other sauropods, like Apatosaurus and Camarasaurus, roamed in herds, their footprints preserved in Wyoming mudstones. These giants weren't just big, they were efficient. Their small heads and peg-like teeth stripped plants quickly, while massive stomachs fermented tough leaves, much like modern cows, per Dr. Martin Sanders' work at the University of Bonn. Why so huge? In the oceans, marine reptiles ruled. Ichthyosaurs, dolphin-like predators, swam in schools, their streamlined bodies and large eyes perfect for hunting fish, per fossils from England's Lyme Regis. Plesiosaurs, with long necks or massive jaws, patrolled deeper waters, snapping up ammonites per Dr. Judy Massari's studies at SUNY Brockport. Plesiosaurs like Leopleurodon, up to 20 feet long, were apex predators, their teeth crushing anything in their path, per French fossils. Ammonites and belemnites, squid-like creatures with hard shells, thrived, their fossils common in Jurassic rocks worldwide. The Jurassic story is written in stone, and the Morrison Formation is one of the best pages. This vast deposit stretching across Wyoming, Colorado, and Utah is a treasure trove of fossils, studied by Dr. Octavio Mateus at Portugal's New University of Lisbon. It reveals sauropod nesting sites with eggs the size of footballs, showing Diplodocus and others laid dozens at a time, per a 2022 paleobiology study. Trackways in Texas and Portugal show herds moving together, some tracks so deep they suggest muddy plains trampled by multi-ton giants. Oxygen isotope studies, like those in a 2019 geology study, confirm the Jurassic's warm, wet climate, with seasonal monsoons watering Pangaea's coasts. Fossilized pollen from Australia shows cycads and ferns dominated, supporting massive herbivores. In China's Yanliao biota, fossils of Anchiornis, a feathered dinosaur, reveal early bird-like traits per Dr. Xu Xing's research at the Chinese Academy of Sciences. These sites paint a picture of a thriving world, where dinosaurs, pterosaurs, and marine reptiles filled every niche. The oceans tell a similar story. England's Jurassic Coast, a UNESCO site, yields ichthyosaur skeletons with preserved embryos showing they gave birth to live young, per a 2020 Science Advances study. Ammonite fossils with their spiral shells show rapid evolution, their shapes changing to suit shifting currents. The Jurassic was a time of stability. No major extinctions disrupted it, letting life diversify like never before. Picture the Jurassic herds of Brachiosaurus lumber across plains, their necks swaying like cranes under a canopy of cycads. Allosaurus stalks in the distance, teeth glinting. Above, Pterodactylus glides, its shadow flickering over a river where ichthyosaurs leap. Archaeopteryx flutters between trees, dodging stegosaurus tails. In the seas, plesiosaurs glide past ammonite swarms, their long necks weaving through turquoise waters. This is a world of giants, from land to sea to sky, where life stretches to its limits. The Jurassic was a turning point. Dinosaurs became the undisputed rulers of the land, pterosaurs owned the skies, and marine reptiles dominated the seas. Pangaea's breakup created new habitats, fueling diversity. Early mammals, still mouse-sized, scurried at night, eating insects, according to fossils from China. They were there, but dinosaurs stole the spotlight. Why didn't these giants evolve complex brains like mammals or later birds? As we leave the Jurassic's lush forests and teeming seas, think about those sauropods, Brachiosaurus diplodocus, towering over the earth, the largest animals ever to walk it. They grew to monstrous sizes, yet their brains stayed small, no smarter than a modern cow. Why did they get so huge, but never evolve modern intelligence? Was it their environment, their biology, or something else holding them back? The answer might reveal why some creatures rule, and others think. Imagine a world where dinosaurs reign supreme, their roars echoing across jungles bursting with flowers. Horned giants clash in dusty plains, while winged reptiles soar above sparkling seas. This is the Cretaceous, the golden age of dinosaurs, a time when Earth feels alive, vibrant, and unstoppable. But beneath the surface, trouble brews, volcanoes rumble, seas rise and fall, and a cosmic threat looms in the darkness of space. For 79 million years, dinosaurs rule a planet that's greener and wilder than ever, but their final sunrise is coming. This is the story of the Cretaceous, a chapter of triumph, diversity, and a catastrophic end that changed everything. Let's dive in and see what made this world so spectacular, and why it couldn't last. The Cretaceous begins 145 million years ago, picking up where the Jurassic left off. The supercontinent Pangaea is breaking apart, and the continents are starting to look familiar. North America is splitting from Europe, the Atlantic Ocean widening, per paleogeographic studies by Dr. Christopher Scotese at Northwestern University. South America and Africa drift apart, creating new coastlines. These shifting plates, studied through fossil distributions in Science 2019, bring warm, wet climates with no polar ice and temperatures 5 to 8 degrees Celsius higher than today, per oxygen isotope data from fossil shells. The biggest game changer on land? Flowering plants or angiosperms explode in diversity. Fossils from China's Yixian Formation, analyzed by Dr. David Dilcher at Indiana University, show early flowers like Archifructus, simple but effective. These plants spread fast, their seeds and nectar attracting insects, per a 2020 Nature Plants study. Forests of magnolias, oaks, and maples replace Jurassic ferns and cycads in many areas, creating lush ecosystems. Pollinators like bees and butterflies evolve, buzzing through Cretaceous jungles, per amber fossils from Myanmar studied by Dr. George Poinar at Oregon State University. This plant boom fuels herbivores, which feed predators, creating complex food webs. The climate, warm and humid, supports swamps, rivers, and coastal plains, per a 2021 geology study. Oxygen levels hover around 21 to 23%, close to modern per Geobiology 2018, giving animals energy for active lives. The Cretaceous is a paradise, but it's also a pressure cooker. Life's diversifying, but the planet's restless. The Cretaceous is the dinosaurs' finest hour. Sauropods like Argentinosaurus from Patagonia still roam, some weighing 100 tons per fossils studied by Dr. Jose Carbalito at Argentina's Museo Egidio Ferruglio. But new stars steal the show. Tyrannosaurs like Tyrannosaurus rex emerge late in the period, their 40-foot bodies and bone-crushing jaws ruling North America, per Montana's Hell Creek Formation fossils analyzed by Dr. John Horner at Montana State University. Early tyrannosaurs like Gorgosaurus were smaller but still deadly, hunting in packs, per a 2022 paleobiology study. Hadrosaurs or duck-billed dinosaurs thrive in herds. Edmontosaurus, up to 40 feet long, munched plants with hundreds of teeth, its fossils common in Alberta's Dinosaur Provincial Park, per Dr. David Evans at the Royal Ontario Museum. Ceratopsians like Triceratops with their horned faces and bony frills, grazed in groups, their skulls found in Wyoming's Lance Formation. These plant eaters use their horns for defense or display, per a 2019 Nature Communications study. Raptors like Velociraptor from Mongolia's Jadokta Formation were small but fierce, with sickle claws and sharp minds. Ankylosaurs like Ankylosaurus waddled with clubbed tails and armored backs, ready to fend off T-Rex per Canadian fossils. The Cretaceous land was a dinosaur showcase from giants to nimble predators, each perfectly adapted. Skies and seas, a world alive. The skies are busier than ever. Pterosaurs like Quetzalcoatlus from Texas had wingspans up to 33 feet soaring like planes over plains, per fossils studied by Dr. Wanda Alexander at Big Bend National Park. These giants scavenged or snatched fish, their lightweight bones ideal for flight, per a 2020 current biology study. Birds diversify, with early species like Confuciusornis from China showing modern feathers and beaks, per Dr. Jingmai O'Connor's research at the Chinese Academy of Sciences. They shared the air with pterosaurs, carving out niches. The oceans are a monster's playground. Mosasaurus, a 50-foot marine reptile hunted with jaws full of conical teeth per Kansas fossils studied by Dr. Johan Lindgren at Lund University. Plesiosaurs like Elasmosaurus swam with flippers and long necks snatching fish per Wyoming fossils. Ichthyosaurs faded, but sharks like Cretoxorina filled the gap, slicing through schools of fish per Alabama fossils. Ammonites with their spiral shells thrived, their fossils common in Europe's chalk cliffs per a 2021 paleobiology study. Sea turtles and early crocodiles swam coastal waters, making the seas a vibrant, dangerous place. Foreshadowing the end. The Cretaceous isn't all sunshine and flowers, signs of trouble loom. In India, the Deccan Traps volcanoes begin erupting around 66 million years ago, spewing lava and gases across what's now Maharashtra, per a 2020 science study by Dr. Gerda Keller at Princeton. These eruptions release carbon dioxide, warming the planet further, and sulfur, which may have caused acid rain. Fossils from India show declining plant diversity, hinting at stress, per Dr. Vandana Prasad's research at the Birbal Sani Institute. Sea levels rise and fall, flooding continents then retreating, per a 2019 geology study. North America's western interior seaway splits the continent, creating a warm, shallow sea from Canada to Mexico, per fossils from Kansas. This seaway teems with life but shifts ecosystems, stressing some species. Climate swings, driven by volcanism and plate tectonics, make the planet unstable, per a 2021 Nature Geoscience study. Pollen and leaf fossils from Alaska show warm forests near the poles, but rapid changes challenge life. Dinosaurs, though, seem unfazed. Nesting sites in Montana, studied by Dr. David Varricchio at Montana State, show Maiasaura cared for their young, leaving eggs and nests in colonies. Trackways in China reveal herds moving together, adapting to change. But the clock is ticking. A 6-mile-wide asteroid, later named Chicxulub, is hurtling toward Earth, undetected in the Cretaceous skies. Real data, the fossil record. The Cretaceous fossil record is a gold mine. The Hell Creek Formation in Montana, studied by Dr. Thomas Holtz at the University of Maryland, yields T-Rex, Triceratops, and Edmontosaurus, painting a picture of late Cretaceous life. China's Yixian Formation, with its feathered dinosaurs like Microraptor, shows the bird-dinosaur link per a 2022 Nature study. Argentina's Neuquén group, home to Argentinosaurus and Giganotosaurus, reveals South American giants per Dr. Rodolfo Correa's work. Oxygen isotope studies from foraminifera fossils, published in Science, 2020, confirm warm, stable climates until late Cretaceous disruptions. Leaf fossils from Wyoming, analyzed by Dr. Kirk Johnson at the Smithsonian, show flowering plants outcompeting conifers, reshaping ecosystems. Marine fossils from Europe's chalk beds like ammonites and mosasaurs reveal thriving oceans, but iridium spikes in the KPG boundary clay, per a 2019 Nature Geoscience study, hint at the asteroid's arrival. A golden age, a fragile world. Picture the Cretaceous, Triceratops lock horns in a flower-strewn plain, their frills flashing. T-Rex roars, chasing a fleeing Edmontosaurus through a swamp. Quetzalcoatlus glides above, its shadow crossing a river where Mosasaurus snaps at fish. Magnolias bloom, bees hum, and ammonites bob in turquoise seas. This is a golden age, dinosaurs at their peak, life bursting at the seams. But volcanoes smoke in India, seas shift, and a cosmic rock approaches. The Cretaceous was a triumph of diversity. Flowering plants and insects reshaped the land, dinosaurs ruled every niche, and birds took flight. But it was fragile. Volcanism, climate swings, and rising seas set the stage for collapse. The Chicxulub asteroid, striking 66 million years ago in Mexico's Yucatan, delivered the final blow, wiping out 75% of species per Dr. Walter Alvarez's research at UC Berkeley. Dinosaurs fell, but birds, mammals, and others survived, ready for a new chapter. Dinosaurs didn't fail. They ruled for over 165 million years, longer than humans have even existed. They shaped the Earth, from forests to seas, leaving a legacy in every bird we see today. If you made it this far, you're one of the curious few who want to know the lost worlds that built our own. Subscribe now, and let's keep digging into the past that made us who we are. As we leave the Cretaceous' vibrant jungles and crashing seas, think about that asteroid, Chicxulub, a cosmic bullet that ended the dinosaurs' reign. It left a crater, a legacy, and a world forever changed. But what if it never struck? Would dinosaurs still rule, smarter and stronger? Would mammals and humans ever have gotten their chance? The answer might make us question our place in Earth's long, wild story. The planet that built us. Take a moment and let it sink in. 600 million years. From soft-bodied jelly creatures drifting in alien oceans to tyrannosaurs roaring under a sky filled with pterosaurs. From a frozen Earth where life barely clung on, to steaming jungles where flowers bloomed and dinosaurs thundered. This planet has been so many things: alien, beautiful, brutal. It's seen oceans rise, continents crack, and life reinvent itself over and over, through explosions of diversity and extinctions that nearly ended it all. Yet somehow, Earth remembers. In the fossils locked in stone, in the layers of rock that tell stories older than any book, in the shape of every creature alive today, including us. The Ediacaran's strange kites, the Cambrian's armored predators, the Devonian's walking fish, the Carboniferous' giant bugs, the Triassic's scrappy dinosaurs, the Jurassic's long-necked giants, and the Cretaceous' final roar, they're all part of our story. Every step, every survivor, every catastrophe shaped the world we walk on now. If this journey through prehistoric Earth changed how you see the world, share it. Pass this story on to someone who's never thought about the 500 million years that built us. And if you want more, subscribe for stories of ancient life, space, and everything in between. Because history didn't start with humans, and it won't end with us. Earth's been telling its story for billions of years, and we're just one chapter. Lucky enough to be here. Curious enough to look back.